Let's do this example of finding a least squares solution, the least squares error vector, and the least squares error of this system, and we will do this using the normal equation for the coefficient matrix. I'll leave a link in the description to a video where I introduce all these concepts, but let's get into this example problem. So here is our system. We have three equations in two unknowns, and just so you know, we're going to end up getting a unique solution to this problem. If you're looking for an example with infinitely many solutions, link in the description. All right, so we're going to try to find a least squares solution of ax equals b, where a is the coefficient matrix from the system, coefficients of x1 in column 1, coefficients of x2 in column 2, and then on the right we have the constants, and we're calling the constant vector b. In order to find the least squares solution, we're going to solve the normal equation, a transpose ax equals a transpose b. This is A, so this is A transpose, and doing the multiplication for A transpose A gives us this 2 by 2 matrix. Just for example, the first entry is 1 plus 1 plus 4, so 6. Then we also need the right side, A transpose B. There's a transpose, there's the constant vector b, and just for example, the first entry is 3 minus 2 minus 2, that's 3 minus 4, so -1. This is the whole vector a transpose times b. So the normal equation, a transpose ax equals a transpose b, is seen here. This is the coefficient matrix, A transpose A, and this is A transpose B on the right. The least squares solution vector is x1, x2. We can represent this system with an augmented matrix, and then perform Gauss-Jordan elimination to solve the system. Performing Gauss-Jordan elimination, you can verify that we arrive at this reduced row echelon matrix. This tells us that x1 equals 29 over 33, and x2 equals 23 over 66. Hence, the unique least squares solution for the system is x equals A transpose A inverse times A transpose times B. That's what we just found. It's this vector with those values of x1 and x2. So that's the least squares solution. We can use this to find the least squares error vector and the least squares error. The least squares error vector is b minus our approximation, ax. That's b, that's a, that's x. A times x is that column vector there. Doing the subtraction gets us this least squares error vector, whose norm, the least squares error, is about 2.41209. So that's an example of using the normal equation to find the least squares solution, least squares error vector, and least squares error for an inconsistent linear system. Let me know in the comments if you have any questions, and be sure to check out my linear algebra course and linear algebra exercises playlists in the description for more. Thanks for watching.
Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about. Stressed out, honey, I've been stressed out lately. Don't know what's what, don't know what I'm stressed about. Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about.